Good morning, class. Today we're going to see the polar forms of conic sections. Now you're probably going to be asking yourself, what the heck is a conic section? Think of it this way. Just assume you have two ice cream cones whose tips are touching. A conic section would be a cut or a cross section of those two three-dimensional objects in any direction. So say, for example, I take a knife and I cut it here, I might end up with something that looks like a circle. If I cut it like this, like top to bottom, I might end up with something that looks like this. And then you can angle it in different directions. So a conic section is pretty much a cross section of these two. Sorry about that. I feel fine, just in case. A conic section is pretty much a cut or a cross section of these two three-dimensional objects in any direction. Now, again, don't freak out. You're not going to be asked to cut it and try to visualize it. This is just a theoretical explanation of what a conic section is. Now, in this chapter, we're going to be working with three different types of conic sections, and you already have worked one of them a lot with me before. The one you guys have worked a lot with is parabolas. Again, depending on how you cut the conic section, you can end up with a parabola. The other two that you don't know are ellipses, which is a somewhat circular structure, not a perfect circle, and also hyperbolas, which are graphs that pretty much open in two opposite directions. Okay, they can be very flat, they can be very, very curved. So it's quite, interesting, hyperbolas. Now, how do I end up with a hyperbola, a parabola, or an ellipsis? Simple. If you recall, when we worked with the parabolas, let's focus just on the parabola first. And then, depending on what answer we get, we're either going to have a parabola, an ellipsis, or a hyperbola. If you remember, when we worked with the parabolas, we had a point called the focus. We also had a line called the directrix. And the whole point of the parabola is that it was graphed in a way that the distance from the focus to the parabola was always the distance from the parabola to the directrix. No matter what points you got, and by the way, this is not drawn to scale. I tried, but you know how I draw. So the whole point of the parabola is that the distance from the focus to the parabola is always the same as that same exact point from the parabola to the directrix. So when you have the same distance from here to here and from here to here, you have a parabola. It's expressed this way, E, or eccentricity. E is pretty much a division from the line PF, or graph to focus, and PQ, graph to line, which might or might not be the directrix in this case. If that ratio gives you the number 1, that means that this line is identical to this line. And when those two lines are identical and you end up with 1, you're looking at a parabola. When E equals 1, it's a parabola. So if this distance, if you have a parabola, and I tell you this distance, or when you have a graph, this distance is 5, this distance is 5, even though it's not drawn to scale, since these two distances are identical, you're looking at a parabola. Okay? Now, let's see what happens when the distances are different. Maybe I have, let's say I have this case, which is flat, and my focus is here. The distance from here to here and here to a line will not be the same as this distance here. So it changes. Again, it's a very mathematical operation. I'm just trying to get you to see that when the ratio changes, you no longer end up with a parabola. Now, what happens when your ratio is bigger than 1? You have a hyperbola. And that happens when the line from the focus to the graph is bigger than from the graph to line that does not contain the directrix. So say, for example, I have this graph, and this is the focus. The distance from the focus to this point is greater than from this point to the line I'm measuring. Since the ratio, you end up with a number bigger than 1, it's 0. And the opposite happens when you have a number between 0 and 1. When you end up with a number between 0 and 1, like a fraction or something else, that's pretty much an ellipsis. Again, I'm not going to ask you to draw certain shapes or to calculate the E as much. This is more or less a theoretical example. When your eccentricity ratio is 1, parabola. When your eccentricity ratio is greater than 1, hyperbola. When it is between 0 and 1, ellipsis. That's pretty much it for the theoretical part. Now let's go over how to write the polar forms of conic equations. Remember, since we're dealing with polar forms, we have to include the letters R and also an angle. Now you'll see at the bottom of page 562, they give you 4 basic, parent functions. Something that looks like this. And you're given 4 different ones with cosine and sine. The basic gist of these 4 functions is that when you're dealing with cosine always opens sideways. If it's positive, it's gonna open this way, like this. If it's negative, it's gonna open to the right, as stated in the book. Also, sine, when you change cosine for sine, it opens up or down. And it's also kind of like the opposite. When you're adding sine, it opens down. When you're subtracting sine, it opens up. And based on what you're looking at, you know already if you should be using cosine or sine. If I give you something that looks like this and you're using sine, you know it's wrong. This has to be actually this one, plus cosine, because it's a cosine that opens to the left. So again, those 4 formulas are the exact same thing. They're only changing plus cosine minus cosine. Again, plus cosine minus cosine, and plus sine minus sine. That gives you a starting point, at least, on where to find your particular polar form of that conic section. Now, let's jump over to the first example, because again, all that was just theoretical mumbo jumbo to kind of introduce the subject. And one thing, these things look scary as heck. This is incredibly one of the easiest classes I've actually taught you guys. If you remember the parabolas, it's kind of like finding the missing variables. It's not that difficult. Let's, for example, go over example 1. In example 1, it says determine the eccentricity, so I have to find my E, type of conic, and equation of the directrix for each polar equation. So I have to find my E, my D, and my type. E is going to be a number, D is going to be a number, type is going to be ellipsis, parabola, or hyperbola. Now let's go over the exact same first example. I'm told that 3 plus 2.25 cosine theta. And under this, I'm going to write the parent function. Okay, now all I have to do in order to find these 2 things and this is take this, transform this to this. Now the easiest way to do this is the following. The number that is constant, which isn't always the first one, you have to order it properly. You have to turn this into a 1. So what is the easiest way to turn 3 into a 1? You divide everything by 3. So you know you're going to divide everything by 3. and you keep that number in your mind, 3. So what do I do now? I'm going to divide the numerator by 3. I'm going to put a 3 outside, and what is 9 divided by 3? 3. What is 3 divided by 3? 1. And what is 2.25 divided by 3? 1. 0.75 que diga. 0.75 cosine theta. So you divide everything by this number. Miren, right? I haven't divided yet. I'm just breaking it down so you can see it. 3 times 1 is 3. 3 times 3 is 9. And you divide this number by 3. You put the answer here. 3 times 0.75 is 2.25. What do I do now? Get rid of my 3's. And I am left with 3 over 1 plus 0.75 cosine theta. Now, let's go over the following items. Since this number here is E, the same thing as this one, but the one down here tells us the eccentricity. So since this is 0.75 and it's a number between 0 and 1, I am actually looking at an ellipsis. Okay. When you have this number, I know that that is ED. Okay. So what you do is, I know that my E is 0.75 because I get the E down here. So in order to find my D, you divide 3 by 0.75. And that gives you an answer of 4. Again, E is 0.75 and I have to find my D. Since this multiplication is equal to 3, I know that my D is 4. And that's it. I found my E, 0.75. I found my D, the number 4, and I found my type, an ellipsis, because E is between 0 and 1. Let's do example B now, or, part B from example 1. I have negative 16 over, see here they give me 4 sine theta minus 2, but I'm going to rewrite it as minus 2 plus 4 sine theta. And again, I got to turn this into a 1. So I'm going to divide everything by negative 2. Okay, so negative 2 times 8 gives me negative 16. Negative 2 times 1 gives me negative 2. And negative 2 times negative 2 gives me 4 sine theta. Yes or no? If I multiply all these negative 2's times everything, I'm going to end up with the original equation. Now, the whole point of doing this is to get rid of a negative 2 at every single item in order to end up with my proper polar form. So I get rid of my negative 2's and I end up with 8 over 1 minus 2 sine theta. Now remember, I already have my E. E is 2. Una cosa. E is 2. The negative, much like reflections, only tells you if it opens up or down. This is a sign, which is negative, so it opens upward. You only look at the number. So my E is 2. The negative, much like polynomial reflections, has to do with up or down. Since the number is 2, 2 is greater than 1, I'm looking at a hyperbola. I know I'm looking at a hyperbola. So I already found my type. I found my type and I found my E. My E is 2 and my type is hyperbola. How do I find my D? Easy. Remember, 1 second. Sorry about that. How do I find my d? This number, e times d, will equal 8. I know that my e is 2, so 2 times d equals 8. Whenever you isolate your d, you end up with d equal to 4, and you're done. Again, the whole point is to have 1 plus something or 1 minus something in the denominator. You're going to be turning that number into 1, and you're going to get rid of the factor you removed from every other term. Okay? Now, let's do the opposite. They're going to give you certain values, and you're going to have to find the polar form. This is even easier because, for example, in example 2, they tell you that E is 2, and they tell you that the directrix is y equals 4. Now, what's important is I'm going to write down my number, or my basic function 1. Now, the tricky part here is knowing whether you're working with sine or cosine, and also if it's positive or negative. Now, if you remember properly, if they tell me the directrix is the line y equals 4. Now, in a coordinate plane, the line y equals 4 would be up here, sideways. So that means my parabola cannot open like this. It has to either open up or open down. So I know I'm working with sine theta. Now the plus or minus, it depends on whether the directrix is above the origin or below the origin. If the directrix is up here, that means my shape has to be somewhere down here. If my directrix were down here, my shape would be somewhere up here. So since it opens downward, that is a plus. That is the trickiest part of this situation. Finding out whether it's sine or cosine, positive or negative. Let's give you guys another example. Let's say they tell you that the directrix is the line x equals negative 3. This is the line x equals negative 3. That means my shape has to be somewhere like this. Since it opens like this, it's minus cosine theta. Make sure you practice that a little bit. That is the most difficult part. Now, oh, I forgot my e here. All you have to do is plug in and you're done. I know that my e is 2 and my d is 4. That means I'm going to have 8 as a numerator, 1, and then I'm going to put your e in front of the identity, and you're done. So again, the only tricky part about finding this is knowing whether to use sine or cosine and positive or negative, and that is solely based on the directrix that you're given. If you're given y's, it's going to be sine. If you're given x's, it's going to be cosine. I wonder where I've seen this before. Y, sine, x, cosine. Interesting. The second part is positive or negative. If it opens up, minus sine. Opens down, positive sine. Opens to the left, positive cosine. Opens to the right, negative cosine. That's pretty much it. Now, if you were to look at example B, you'd say, Profe, but that one's incredibly large. I mean, look at all the numbers they're giving me. It's the exact same thing. The only difference is instead of giving you the directrix, or instead of them giving you the distance, they're actually giving you two vertices, or the vertex and another point. They're giving you coordinates, and all you have to do is use the distance formula between those 2 points to find your d, and the exact same process. If you don't remember the distance formula, make sure you review it, because that's not part of today's class. Find your d. Either they're going to give it to you, or you're going to use the distance formula, plug it in, make sure you put sine or cosine properly, and you're done. And we're going to leave example 3 for tomorrow, because that one is kind of tricky, and let's take it one step at a time. So for today, please do the exercises 1 through 4 and 10 through 13. send the pictures online, and I'll be taking attendance later on at 10 p.m. One thing, your grades. I'm going to be uploading your grades today and tomorrow. I'm going to be uploading a whole bunch of grades. The classes that we did last week are actually going to be the substitute for the notebook of the third quarter, because it's either that or having no notebook grade. So in order to have something for notebook, it's going to be the homeworks that you guys did last week. There's nothing else we can do. I'm going to be uploading the PBLs, both the bonus grade and the reports, which not everybody turned in on time or at all. One group didn't turn in time neither of the times. So I'm going to be uploading the PBL report, the PBL showcase, the PBL extra grade, the exams I have here, a formative that we did, and also the notebook. That's it. Have a great day, and if you have any questions, class and answer 4.